My name is Prithvisha Nath and I am TA for this course, Vibration of Continuous System. I am a PhD student in the Department of Aerospace Engineering at IIT Madras. This is week 6 for this course. So let us start solving the problems. So for the first problem, it is said the problem is find the steady state response of a pinned beam subjected to a harmonic force applied at x equals to a. So for this question we need to find the steady state response. Now so this is the diagram. This distance is a, and this is L. So we need to find the steady state response of this beam. So we know that for forced vibration solution, forced vibration the solution of a beam can be determined using mode superposition technique. So we can assume the deflection of the beam to be small w x comma t equals to n equals 1 to infinity omega capital W n x t. Here capital W x is called the normal mode. Q and T is the generalized coordinate in the nth mode. So for this problem, we can use this method to solve the problem. So for the normal mode function is given by sine of beta nx, which is equals to sine of n pi x by L. Now, therefore we can say beta, now here we can say that beta nl equals to n pi. Now, the generalized force Q and T is given by 0 to L f x comma t w nx dx. So we can write this as Q and T for this problem becomes f naught sine n pi a by L sine of omega t. Now, what is the steady state response of the beam? The steady state response of the beam is given by one by rho a b omega n 0 to t q n tau sine omega n t minus tau d tau. Now where B is B we know is 0 to L omega n square x dx. Now sorry, wn square, not omega, w square x dx. So w here is sine beta nx. So if I write sine square beta nx dx, so what will I get? I can write this as 1 minus cos 2 beta nx by 2 uh, so this is 0 to L. If I integrate this, I will get this to be L by 2. Now I just need to substitute this value for B in this expression of Q and T. Now Q and T becomes 1 by rho A. In place of B, I will substitute it as L, and this 2 goes to the numerator. So 2 by rho AL. Now this expression can be written as sine of n pi a by L omega n square omega square sine of omega t. After solving this this part and substituting the value of b, finally we get Qn as this. Now what is the response of the beam? Response of the beam is given by small wx. Response of the beam is small w x comma t. And what was that? That was given by capital W and x, q and t. So I know both. So that becomes F naught rho AL summation from n equals 1 to infinity. Now first I'll write the value for Qn, 1 by omega n square minus omega square into sine of n pi a by L. Now sine of omega t into Wx. So Wx was sine n pi x by L into sine of n pi x by L. So this is the response of the beam. Now moving on to the next problem. A steel cantilever beam of diameter 2 cm and length 1 meter is subjected to exponential decaying force 100 e to the power minus of 0.1 t Newton at the free end. Determine the steady state response of the beam and assume the density and Young's modulus of steel as the given values. So here we have a cantilever beam which is subjected to an exponentially decaying force at the free end. So this is the problem. It is of 2 cm diameter and Ft is given as 100 e to the power minus 0.1 t and the length is 1 meter. This length is 1 meter and the diameter is 2 centimeter. So what is given? Given density is 7500 kg per meter cube and Young's modulus is given as 210 into 10 to the power 9 Newton per meter cube. So again we know that I can write this small w as x comma t summation of n from n equals 1 to infinity, capital W n x q n t. Now for a cantilever beam, Wn is given as Cn into sine beta nx minus sine hyperbolic beta nx minus alpha cos beta nx minus cos hyperbolic beta nx. Where alpha can be written as sine of beta nl plus sine hyperbolic beta nl divided by cos of beta nl plus cos hyperbolic of beta nl. Now we know that the generalized coordinate can be written as the generalized coordinate is given by this equation. Equals to 1 by rho a b qn time, where again we know that capital Q can be written as 0 to L f x comma t wn x dx. So this is equals to capital F and wn L. Now the steady state solution of this equation. Suppose this is my equation 1. Now the steady state solution of equation 1 can be denoted by equation 1 is given by one by rho a b omega n 0 to t qn tau sine omega n t minus tau d tau. Now it can be shown that b, which is equals to 0 to L omega m square x dx equals to L. Now if I substitute this value in the expression for small qn, what do I get? Now first I will solve this integral. Zero to t qn tau. First I'll solve this integral. Sine omega n t minus tau d tau equals 100. I'm just substituting the values. 100 omega nl 0 to time t e to the power of this comes from my ft term. This ft term. This is tau sine of omega n t minus tau d tau. Now finally, after solving this, qn can be solving the integral we get, and substituting it in the formula for small qn, we get it as 100 wn l rho a l omega n into omega n square plus 0.01 and omega n e to the power minus 0.1 t plus 0.1 sine of omega n t minus omega n cos of omega n t. Now next what should I do? Now I know rho is, now I'll put the value for rho. Rho is kg per meter cube. Length is 1 meter and area I can calculate from the diameter, that is pi by 4 into 0.02 whole square. Now this comes out to be pi by 4 into 0.02 whole square, that is 3.1416 into 10 to the power of minus 4 meter square. Now finally, if I substitute all this value, I get Qn as 42.4412 omega nl divided by omega n into omega n square 0.001 and the rest of the term, that is omega n e to the power of minus 0.1 t plus 0.1 sine of omega nt minus omega n cos of omega n t. Now this is the expression for Qn. Now moving on to the next problem. Find the steady state response of a cantilever beam that is subjected to a suddenly applied step bending moment of magnitude m0 at its free end. So here again I will assume the solution to be the solution is assumed to be small wx comma t equals to capital W nx q n t. Now this is the problem. So here m0 is applied at the free end and this is the length of the cantilever beam. Now the generalized force Q and T is given by m naught dWn dx at x equals L. And we already know the steady state response is given by small qn. So the steady state response is given by qn 1 by rho ab omega n 0 to t capital Qn tau sine of omega n t minus tau d tau. Now in place of Qn, I will substitute this value which I have. Now substituting Qn, this becomes 1 by rho ab omega n 0 to t. Now this I can take outside the integral, outside. So m naught dx at x equals L sine of omega n t minus tau d tau. Now here it can be shown that the value of b, which is equals to capital Wn square x dx, is equals L. Now what is the value of b? B is 0 to L omega n square x dx. This can be shown to be L. Now I just substitute again in place of b. And what is the value of integral sine omega n t minus tau d tau? I can write this as cos of omega n t minus tau from 0 to tau divided by 1 omega n. Now putting the limits, this becomes 1 like cos of omega n tau minus tau minus of cos omega n t. So this finally becomes 1 by omega n 1 minus cos of omega n t. Now finally I will substitute all the values into this expression of Qn. Now after I substitute, I can Qn becomes so Qn becomes m naught rho a. In place of b I will put L omega n square dWl dx at x equals L into minus of 1 minus cos of omega n t. So this is the solution. Now the next problem, in the next problem we have to find the response of a simply supported beam subjected to a uniformly distributed harmonically varying load. So what can we do? The equation of motion can be written as EI plus rho A del T square equals F naught sine of omega t. So we can assume small w x comma t equals to w x sine of omega t. Now I will substitute this equation. Suppose this is my equation number 1, this is equation number 2. Now I need to substitute this in equation number 1. I'll differentiate this. So what will I get? I will get this as sine of omega t, and if I differentiate with respect to time, what will I get? Capital Wx cos of omega t into omega, again differentiating it with respect to time, this gives minus of omega x sine of omega t. Now I will substitute this in equation number 1. Substituting in equation number 1. I will get this as EI sine of omega t minus of omega square w sine of and yeah, rho a is also there. So first I will write that minus rho a omega square w sine of omega t equals to f naught sine of omega t. Now this can be written as, I will take the Ci to the denominator, so rho a by EI omega square w divided by equals to f divided by EI. Now I will assume EI by rho a equals to C. C equals to C square equals to EI by rho a. Now this equation will become as dx to the power 4 minus 1 by C square, omega is also there, omega square w f naught by C square into rho into a. This is the equation number 3. So how can I write the complete solution for capital Wx? I can write this as the complete solution for equation 3 is Wx equals to C1 of cos beta x plus C2 of sin beta x plus C3 of cos hyperbolic beta x plus C4 of sin hyperbolic beta x minus f naught rho a into omega square. Now what can I do next? Here beta is omega square by C square. Beta square is omega square by C square. Now what can I do next? I can apply the boundary conditions. Now the boundary conditions for a simply supported beam is at x equals 0, it is 0. Now also w at x equals l is 0, and this is also 0. Now let this be. Now using this I can substitute in the equation number, this equation. Suppose this is equation number 4. Now substituting let this be 5 so this is 6 7 8. Now I will substitute equation 6 in equation number 4. Substituting equation 6 in equation number 4. So this is equation number 4. Now if I substitute this x equals 0, at x equals to 0, w 0, so what will I get? 0, x is also 0, so c1 plus c3 minus of a f naught rho a omega square 0. So this is one more equation which I get. Let this be 10. Now substituting equation 7 in equation number 4, we get substituting 7 in equation number 4, what we get? minus C1 beta square plus C3 beta square basically we need to differentiate this equation for Wx twice and then we need to substitute. So after substitution what we get is C1 beta square plus C3 beta square equals 0. This implies that C1 equals C3. Now again what I can write from equations from equation 10 what can we write? Since C1 equals to C3, therefore I can write now since C1 equals to C3, C1 plus C1 equals to F naught rho A omega squared, that implies C1 equals to F naught divided by 2A rho omega squared. This is also equals to C3. So this is another condition which I get. This let this be 11 and this is 12. So now what I do, I substitute equation 8 in equation number 4. I substitute the boundary condition, that is omega W at x equals L equals 0 in the equation, in the complete solution. So what will I get? Now substituting equation 8 in equation number 5, this will give so what is equation W is 0 at x equals L. Now I'll first write the equation again. I'll write this equation again. Wx equals C1 cos of beta x plus C2 sine of beta x plus C3 cos hyperbolic beta x plus C4 sine hyperbolic beta x minus F naught rho A omega square. Now I will substitute this Wx at x equals L equals 0. Now if I substitute this, and I also know that C1 equals to C3, so I will write C3 cos of beta L plus C2 sine of beta L plus C3 cos hyperbolic beta L plus C4 sin hyperbolic beta L minus F naught rho A omega square. Now what I'll do is F naught rho A omega square equals to C3 I already know, so I'll take C3 as common, cos of beta L plus cos of hyperbolic beta L and terms for C2 and C4 is unknown. Like the coefficient C2 and C4 are unknown, so I'll write them down. C2 sine of beta L plus C4 sine hyperbolic beta L. Now I will take this that on the left hand side, F naught rho A omega square minus of C3 is known to be F naught 2A rho omega square into cos of beta L plus cos hyperbolic beta L. This is equals to C2 sine beta L plus C4 sine hyperbolic beta L. Now I will take this, rearrange the equation. Now if I take F naught minus of F naught rho A omega square common, then what will I get? This comes out to be cos of beta L plus cos of hyperbolic beta L divided by 2 minus of 1. This is another equation. I can write this as 5. Equation number 13. Now again I will substitute equation number 9 in equation number 4. Substituting equation 9 in equation 4. What I have to do for this thing, I need to differentiate it twice and substitute for x equals L. Now I will again write the expression for W and then differentiate it twice. This is not exactly equation number 9. I need to substitute uh, this. Here also we did the same. So equations 7 and 4. 7 is this 7 and 4 gives provides. This was also done by differentiating it twice. Differentiating the expression for W twice. Now my expression for W is Wx is given as C1 cos of beta x plus C2 sin of beta x plus C3 cos hyperbolic beta x plus C4 sin hyperbolic beta x minus f naught rho a omega square. Now I need to differentiate this once. This will come out to be minus C1 beta sin of beta x plus C2 beta cos of beta x so this will give C3 beta sin hyperbolic beta x plus C4 beta cos hyperbolic beta x. Again differentiating this, minus C1 beta square cos beta x plus C2 beta square sin of this will be minus beta x plus C3 beta square cos hyperbolic beta x plus C4 beta square sin hyperbolic beta x. Now equations 9 and 4 provides minus C1 beta square cos of beta L. I will write this as C3 since C1 and C3 are equal. Now minus C3 beta square cos of beta L minus C2 beta square sine of beta L plus C3 beta square cos hyperbolic beta L plus C4 beta square sine hyperbolic beta L equals 0. Now C3 I will take as common, so this will give minus cos of beta L minus cos hyperbolic beta L minus C2 sine of beta L plus C4 sine hyperbolic beta L equals 0. Now again I'll rearrange this equation. Minus C2 sine of beta L plus C4 sine hyperbolic beta L gives C3 cos of beta L minus cos hyperbolic beta L. Now in place of C3 I will substitute the value which we got. So minus C2 sine beta L plus C4 sine hyperbolic beta L. In place of C3 I will substitute this value f naught by 2, f naught divided by 2a rho omega square f naught 2a rho omega square cos beta L minus cos hyperbolic beta L. So this is equation number 14. Now solving equation 13 and 14, I can get the coefficients C2 and C4. Now C4 comes out to be F naught by 2 rho A omega square sine hyperbolic beta L 1 minus cos hyperbolic beta L that is equals to minus of F naught uh, and C 2 comes out to be minus of F naught 2 rho A omega square sine of beta L 1 minus cos of beta L So if I substitute this in the final expression, of w, small w, that is wx sine of omega t so wx was c1 plus c1 cos of beta x plus c2 sin of beta x plus c3 cos hyperbolic of beta x plus c4 sin hyperbolic of beta x minus f naught rho a omega square. Therefore, small w x comma t will be now I'll take c1 and c3 common, so that was equals f naught 2 rho a c square, c1 and c3 2 rho. If I take common, cos of beta x plus cos hyperbolic beta x, and in place of C2 I will substitute minus f naught sin beta x plus, for C4 it will be f naught 2a omega square sin beta l, sin hyperbolic beta l. So this will be f naught divided by 2 rho a omega square sin hyperbolic beta l one minus cos hyperbolic beta l into C4 sin hyperbolic beta x minus f naught rho a omega square into sine of omega t. This is the final expression for small w. So for the first problem, what we did, we had to find the steady state response of a pinned beam subjected to harmonic force applied at A. So we assumed we used mode superposition method for this problem, where capital Wn is the nth normal mode and q and t is the generalized coordinate in nth mode. Now for a pinned beam, the normal mode function is given by Wnx equals to sine of beta nx, which is equals to sine n pi x. Now from this we can say that beta nl equals to n pi. Now the generalized force term is calculated by this expression. which is given as F naught sine n pi L sine omega t Now we know the formula for steady state response. The steady state response is given by this formula. We substitute this. We calculate B, which comes out to be L by 2, and from there we substitute it in the expression for Qn, and then we write the solution for small w. Now for the next problem, the cantilever beam, which is of 2 cm diameter and 1 meter length, was subjected to an exponentially decaying force at the free end. Here also we need to find the steady state response of the beam. Here also we did the same thing. For a cantilever beam, Wn is given by this expression, and the generalized coordinate is given by this equation. So from here we calculate capital Qn, and then we finally get small qn after substituting all values. In the next problem, the cantilever beam was subjected to a suddenly applied step bending moment m naught. Here also we did the same thing. Here Qn was given by m naught dw by dx at x equals n L. So we substitute the value of qt in small expression for small qt. We calculate the value for b, which comes out to be L. Similarly, the value of this integral comes out to be 1 minus cos of omega n t divided by omega n, and after substituting we get the value of qn. That is the generalized value for qn. Now for the next problem, we are asked to find the response for a beam subjected to a uniformly distributed harmonically varying load. So we can write the equation of motion as follows. So we assumed Wx to be capital Wx into sine of omega t. We differentiate this with respect to x first and then with respect to time, and then we substitute this in equation number 1. Then we assume this parameters ei by rho a as c squared, and write the equation in terms of c squared, and the complete solution for the equation is written as this, where beta square equals to omega square by c squared. Now we have several boundary conditions, 4 boundary conditions. One by one we put in these conditions in the equation, which gives us the coefficients c1, c3, c2 and c4. Now if we substitute equation 6 in equation 4, we got that c1 equals to c3. Similarly, equation 7 and equation 4 gives us the condition, equation 6 and 4 gives us the condition that c1 plus c3 is equals to f naught by rho a omega square. Now equation 7 and 4 gives us that c1 equals to c3. So what we can say, c1 equals to c3 equals to f naught divided by 2a rho omega square. Now what I do, I substitute equation number 8, this condition w at x equals l equals 0. Substituting this in equation number 4. This should be equation number 4. So after substituting, what we get is, we get this equation, c2 sine beta l plus c4 sine hyperbolic beta l equals to minus of f naught rho a by omega square cos of beta l plus cos hyperbolic beta l divided by 2 minus 1. Now again, equations 9 and 4 provides this solution, gives us equation 14. Now we have two unknowns, c2 and c4, which we need to find out. So by solving equation number 13 and 14, we get equation c4 as f naught divided by 2 rho a omega square into sine hyperbolic beta l whole multiplied by 1 minus cos hyperbolic beta l, and so c2 as minus f naught rho a omega square sine of beta l. Now finally I substitute everything and get the expression for small wx. So these are the problems that we solved for this week.